Tsunamis are some of the most powerful and destructive forces of nature, capable of reshaping coastlines and causing widespread devastation. But how do they form? What causes these massive waves to suddenly appear? Understanding the science behind tsunamis is key to not only grasping their power, but also to being able to prepare for and minimize their impact. Tsunamis aren't like the regular waves you might see at the beach. These waves are much larger and far more dangerous, and their formation starts deep beneath the ocean's surface. Unlike normal waves, which are driven by wind, tsunamis are usually caused by sudden, massive changes in the ocean floor. This can happen for a variety of reasons, but the most common cause is underwater earthquakes. When an earthquake occurs beneath the ocean, the Earth's crust shifts dramatically. This shift can displace an enormous amount of water, creating a series of waves that spread out from the point of the earthquake. These waves can travel at speeds of up to 500 miles per hour across the open ocean, making them extremely fast and difficult to detect. In fact, even though a tsunami can be triggered miles from shore, it often goes unnoticed until the waves start to approach land. What's unique about these waves is that even though they travel incredibly fast, their height is relatively small in deep water, often only a few feet tall. This is why in the open ocean, ships and boats won't notice a tsunami, as the waves pass beneath them without causing much disruption. But as the waves get closer to shore, the water begins to slow down and the waves begin to grow in height. This is where the real danger lies. When the tsunami reaches the coastline, the water can surge hundreds of feet into the air, creating massive walls of water that crash onto the land. The biggest challenge with tsunamis is their unpredictability. While we have some understanding of the factors that cause them, we still don't know exactly when or where they will occur. And even though we know what triggers tsunamis, there's no real way to predict exactly how big they will be or how far they will travel. This makes it extremely difficult to prepare for their impact, as there's often little to no warning before they strike. The effects of a tsunami can be catastrophic. When a tsunami hits land, it doesn't just cause damage from the waves themselves, but it can also trigger flooding, erosion, and destruction of infrastructure. Coastal communities are particularly vulnerable as the waves can travel miles inland, sweeping away homes, buildings, and anything else in their path. Even more concerning is the potential for massive loss of life, especially in densely populated areas. And one of the most devastating examples of a tsunami occurred in December of 2004 when a powerful earthquake off the coast of Indonesia triggered a massive tsunami. This tsunami affected countries across the Indian Ocean, including Thailand, Sri Lanka, and India. The waves reached as far as Africa, and more than 200,000 people lost their lives as a result. The 2004 Indian Ocean tsunami serves as a tragic reminder of just how dangerous and unpredictable these natural disasters can be. The impact of tsunamis can extend far beyond the immediate coastline, affecting global trade, tourism, and commerce. In the wake of a tsunami, it can take months or even years for affected areas to recover. So understanding how tsunamis form and recognizing the warning signs is crucial for minimizing their impact and saving lives. Now that we've covered the basics of tsunami formation, we'll dive deeper into the factors that contribute to these massive waves, including underwater earthquakes, volcanic eruptions, and landslides. In the previous part, we explored the basics of tsunamis, but now let's dive deeper into one of the main causes of these devastating waves, underwater earthquakes. These natural events play a major role in generating tsunamis, and understanding how they work can shed light on the formation of these powerful waves. Underwater earthquakes occur when the Earth's tectonic plates shift, usually along fault lines beneath the ocean. The Earth's crust is made up of large, rigid plates that float on the semi-fluid mantle underneath. These plates are constantly moving, and when they collide, slide past one another, or separate, it causes stress to build up along fault lines. Eventually, the pressure becomes too great and the plates suddenly shift, releasing massive amounts of energy in the form of an earthquake. When an earthquake occurs beneath the ocean, the ground can move up or down, displacing the water above it. This sudden displacement is what generates the waves that we know as tsunamis. The size of the tsunami depends on several factors, including the magnitude of the earthquake, the depth of the earthquake's epicenter, and the type of fault movement. For example, a vertical shift in the ocean floor is more likely to displace large amounts of water, creating a higher tsunami wave compared to horizontal movements. The bigger the shift, the more water gets displaced, and the larger the tsunami can become. This is why more powerful earthquakes, such as those with a magnitude of 7 or higher, are more likely to trigger large tsunamis. One important thing to understand is that while the earthquake itself may only last for a few seconds or minutes, the resulting tsunami waves can continue to travel for hours. These waves can affect vast areas, crossing entire oceans and hitting multiple coastlines before they dissipate. The energy from the earthquake spreads across the ocean, causing a chain reaction of waves that grow in height as they approach the shore. Another critical factor in tsunami formation is the location of the earthquake. Tsunamis are most commonly triggered by earthquakes that occur along subduction zones, where one tectonic plate is forced beneath another. These areas are often located along the Pacific Ring of Fire, a region known for frequent earthquakes and volcanic activity. Countries like Japan, Chile, and Indonesia are especially vulnerable to tsunamis due to their proximity to these subduction zones. A classic example of a tsunami triggered by an underwater earthquake is the devastating event that occurred on December 26, 2004. A massive earthquake with a magnitude of 9.1 struck off the coast of Sumatra, Indonesia, causing the ocean floor to shift dramatically. This earthquake generated a tsunami that affected countries across the Indian Ocean, including Thailand, Sri Lanka, and even parts of Africa. The waves reached heights of over 30 meters in some areas, causing widespread devastation and loss of life. While underwater earthquakes are a significant cause of tsunamis, they are not the only factor at play. Other events, like volcanic eruptions and underwater landslides, can also trigger tsunami waves. In the next part, we will explore how these factors contribute to tsunami formation and the effects they can have on coastal areas. Stay tuned. In the previous part, we looked at how underwater earthquakes trigger tsunamis, but now let's explore two other powerful forces that can cause tsunamis: volcanic eruptions and underwater landslides. Both of these events can displace massive amounts of water, leading to waves that can travel across the ocean and cause significant damage to coastal areas. Volcanic eruptions can be another key trigger of tsunamis, especially when they occur beneath the ocean. While we usually associate volcanic eruptions with lava flows and explosive ash clouds, when they happen underwater, they can create massive disturbances in the water above. One way that volcanic eruptions trigger tsunamis is through the collapse of a volcanic island or underwater caldera. A caldera is a large bowl-shaped crater that forms when a volcano collapses after an eruption. When the volcano's magma chamber empties, the pressure from the underlying layers of earth can cause the seafloor to drop rapidly, displacing huge amounts of water. This sudden drop in the seafloor can send waves racing across the ocean, much like the waves created by an earthquake. Another way that volcanic eruptions can cause tsunamis is through pyroclastic flows. These fast-moving, hot mixtures of ash, gas, and volcanic debris can travel at high speeds across the ocean surface. When they enter the water, they displace large amounts of water, generating waves. These waves may not be as large as those created by an earthquake or a caldera collapse, but they can still cause significant damage along coastlines. A notable example of a volcanic eruption triggering a tsunami occurred in August of 1923 in Japan. A violent eruption of the Sakurajima volcano created pyroclastic flows that traveled into the sea, displacing enough water to create tsunami waves that caused significant damage to nearby coastal communities. Underwater landslides, also known as submarine landslides, can also be responsible for generating tsunamis. These landslides happen when large amounts of sediment, rocks, or debris move suddenly down the continental slope or underwater slopes. The displaced material causes the water above it to move rapidly, creating waves that can travel across the ocean. Submarine landslides can occur for several reasons, including earthquakes, volcanic activity, or even the buildup of excess water in an area. These landslides are often triggered by the destabilization of the seafloor, which can occur when an underwater earthquake shakes loose sediment and rock. In other cases, volcanic eruptions or underwater mining operations can also displace material, triggering landslides. One infamous case of a tsunami caused by an underwater landslide took place in 1998 off the coast of Papua New Guinea. A massive landslide, triggered by an undersea earthquake, sent waves of up to 10 meters high crashing into the nearby coastline, resulting in over 2,000 deaths and widespread damage. Submarine landslides are often harder to predict than earthquakes or volcanic eruptions. making them a significant threat in areas where underwater slopes are unstable. They can occur suddenly and without warning, adding to the complexity of tsunami forecasting and preparation. In the next part, we will explore the effects of tsunamis and how they impact coastal communities from the first signs of a tsunami to the aftermath of a devastating wave. Stay tuned for more on this powerful natural phenomenon. Now that we've explored the science behind how tsunamis form, it's time to take a closer look at their impact and the importance of preparation. Tsunamis can be one of the most devastating natural disasters, capable of causing massive destruction in a very short amount of time. While the waves themselves can arrive quickly, the damage they leave behind can last for years, affecting entire communities and economies. When a tsunami hits, the first wave is often not the largest, and multiple waves can follow. These waves can travel across vast distances, and the time between waves can range from minutes to hours. The waves can be extremely powerful, reaching heights of up to 100 feet or more. Depending on the size of the event, the force of the water can cause buildings to collapse, sweep away vehicles, and flood entire cities. Coastal areas are especially vulnerable as they are directly in the path of the waves. The damage caused by a tsunami isn't just physical. The waves can also severely impact the environment, destroying marine ecosystems, beaches, and vital coastal habitats. The displacement of water can lead to changes in local water quality, and the debris carried by the waves can spread pollutants. In the aftermath of a tsunami, the economic costs can be enormous, especially for communities that rely on tourism, fishing, or trade for their livelihood. In addition to the immediate destruction, tsunamis can leave long-term effects that persist for years. Communities often face rebuilding efforts that can take decades, and many people are displaced from their homes either temporarily or permanently. It can take a long time for people to return to their normal lives, and recovery efforts can be hindered by damaged infrastructure, lack of resources, and challenges in coordinating aid. Despite the devastation caused by tsunamis, there are ways to mitigate their impact. One of the most important factors in minimizing the destruction of a tsunami is early warning systems. Tsunami warning systems rely on networks of sensors placed on the ocean floor to detect changes in water pressure caused by earthquakes or underwater landslides. When a potential tsunami is detected, warnings are issued to coastal communities, giving them time to evacuate to higher ground. Tsunami evacuation plans and drills are essential for preparing people for these events. Communities in high-risk areas must have clear evacuation routes and safe zones, and local authorities must ensure that residents are educated on what to do if a tsunami occurs. The quicker people can evacuate, the more lives can be saved. Another important factor in minimizing the impact of tsunamis is effective building codes and infrastructure design. In areas where tsunamis are a known risk, buildings should be constructed with materials and designs that can withstand the force of the waves. Coastal barriers, like seawalls or floodgates, can also help protect vulnerable areas from flooding. Tsunamis are unpredictable and can strike at any time, but through increased awareness, preparation, and the use of technology, we can reduce their devastating effects. By studying past events and improving our understanding of tsunami formation, we can develop better strategies for both prevention and recovery. Understanding how tsunamis form and their potential impact is essential for preparing communities and saving lives. If you're interested in learning more about natural disasters and how they shape our world, be sure to check out my next video. Stay safe, and remember that preparedness is key when it comes to surviving a tsunami. Tornadoes are one of the most powerful and unpredictable weather events on Earth. These violent windstorms can form quickly, destroy entire neighborhoods in minutes, and leave behind paths of devastation. But how exactly do they form? The answer lies in the right combination of weather conditions all coming together in just the right way. A tornado starts with a thunderstorm, but not just any thunderstorm. Most tornadoes form from a type of storm called a supercell. These massive rotating storms can grow to be over 10 miles wide and last for several hours. The key ingredient in supercells is wind shear, which happens when winds at different altitudes blow at different speeds or directions. This causes the air to start rotating horizontally, forming an invisible spinning tube in the atmosphere. At the same time, warm, moist air from the ground rises into the storm, while cooler air sinks down. This process tilts the rotating air from horizontal to vertical, creating a powerful updraft. If this updraft is strong enough, it stretches and tightens the rotating air, increasing its speed. Over time, this spinning air column extends downward from the storm cloud, eventually touching the ground and becoming a tornado. Tornado formation is influenced by temperature and humidity differences. Warm, moist air from the Gulf of Mexico and cool, dry air from Canada often collide in the central United States, creating ideal conditions for tornadoes. This region, known as Tornado Alley, experiences hundreds of tornadoes every year. However, tornadoes can form in many parts of the world, from Europe to Australia and even parts of South America. Not every supercell produces a tornado, but when the right conditions align, the results can be devastating. Some tornadoes last only a few minutes, while others can stay on the ground for over an hour, carving a destructive path miles long. In the next part, we will look at what happens inside a tornado and how scientists measure their power. Once a tornado forms, it becomes a rapidly spinning column of air that can reach incredible speeds and cause widespread destruction. But what exactly happens inside a tornado, and how do scientists measure its strength? At the core of a tornado is an area of extremely low pressure. As the surrounding air rushes in to fill this pressure gap, it spirals upward at high speeds. The rotation within the tornado is so intense that it can lift heavy objects, rip apart buildings, and even pull trees from the ground. Wind speeds inside a tornado can range from less than 70 miles per hour and weaker ones to over 300 miles per hour in the most extreme cases. The faster the rotation, the more destructive the tornado becomes. Scientists use the Enhanced Fujita Scale, or EF scale, to measure the strength of a tornado. This scale ranks tornadoes from EF0 to EF5 based on the damage they cause. An EF0 tornado has winds between 65 and 85 miles per hour and usually results in minor damage, such as broken tree branches and small roof damage. On the other hand, an EF5 tornado with winds over 200 miles per hour can level entire buildings, toss vehicles, and leave nothing but a bare foundation behind. Since wind speeds inside a tornado are difficult to measure directly, meteorologists assess the destruction left behind to determine the tornado's rating. One of the most dangerous aspects of a tornado is the debris it carries. Flying debris, such as wood, metal, and glass, can turn into deadly projectiles, causing injuries and fatalities. Tornadoes can also create powerful suction forces, making objects appear as if they were thrown in multiple directions at once. Some tornadoes are strong enough to lift large trucks and even small buildings off the ground. While tornadoes are often associated with dark, swirling funnels, not all of them are easily visible. Some tornadoes, especially those forming at night or in heavy rain, can be nearly invisible until they are right on top of a location. This is why tornado warnings and early detection systems are so critical. In the next part, we will explore how tornadoes move, why some last longer than others, and what meteorologists are doing to improve forecasting and safety measures. Tornadoes are unpredictable and can change direction, speed, and intensity in a matter of minutes. But what determines how a tornado moves? And why do some last only a few minutes while others persist for over an hour? The movement of a tornado is controlled by the larger storm system that creates it. Most tornadoes form within supercell thunderstorms, which are massive rotating storm systems driven by powerful winds in the atmosphere. These winds, known as steering winds, push the storm and its tornado in a specific direction. In the United States, for example, many tornadoes traveled from southwest to northeast due to prevailing wind patterns. However, some tornadoes can suddenly shift directions or even move in loops if the wind conditions change. The lifespan of a tornado depends on several factors, including the strength of the storm, the stability of the rotating air, and the availability of warm, moist air near the surface. Weak tornadoes may last only a few minutes before losing energy and dissipating. However, stronger tornadoes, especially those formed by long-lasting supercells, can stay on the ground for over an hour and travel dozens of miles. One of the longest-lasting tornadoes on record, known as the Tri-State Tornado of 1925, traveled over 200 miles across Missouri, Illinois, and Indiana, remaining on the ground for more than 3 hours. Tornadoes can also vary widely in size. Some are narrow, with a width of less than 100 feet, while others can stretch more than 2 miles across. The widest tornado on record occurred in Oklahoma in 2013, measuring an astonishing 2.6 miles across at its peak. A tornado's size does not always indicate its strength, but larger tornadoes often cover a greater area and can cause more widespread destruction. Understanding tornado movement is essential for improving tornado warnings and forecasting. Meteorologists use radar technology to track the formation and path of tornadoes in real time. Doppler radar, in particular, helps scientists detect rotation within a storm before a tornado even touches the ground. By studying past tornadoes and analyzing weather patterns, researchers continue to develop better prediction methods to give people more time to take shelter. As we wrap up, we will look at how tornadoes eventually come to an end, what factors cause them to weaken, and the safety measures that can help protect lives when a tornado strikes. Tornadoes are among the most powerful forces of nature, but they do not last forever. Every tornado eventually weakens and disappears. But what causes this to happen? A tornado begins to dissipate when the conditions that sustain it start to change. The rotating column of air inside a tornado needs a steady supply of warm, moist air from the ground to keep spinning. If this flow is disrupted, such as when cooler, drier air gets pulled into the system, the tornado starts to lose strength. Additionally, changes in the structure of the parent thunderstorm can weaken the tornado. If the storm begins to collapse or move into an area with less atmospheric instability, the tornado will become less organized and eventually break apart. The process of tornado dissipation often follows a pattern. The funnel cloud may begin to narrow and stretch, resembling a thin rope. This stage, known as the roping out phase, is when the tornado becomes weaker and less stable. However, even a weakening tornado can still produce dangerous winds and cause destruction until it fully disappears. Some tornadoes break apart quickly, while others slowly wind down over several minutes. Once a tornado ends, the damage it leaves behind is often analyzed to determine its strength. Scientists use the Enhanced Fujita scale, or EF scale, to rate tornadoes based on the severity of the destruction they cause. This scale ranges from E.F-0, which indicates minor damage, to E.F-5, which represents catastrophic destruction with winds exceeding 200 miles per hour. By studying damage patterns, researchers can estimate wind speeds and learn more about how tornadoes interact with different environments. Because tornadoes can be unpredictable, knowing how to stay safe is crucial. Tornado warnings are issued when a tornado has been detected, and people in the affected area are urged to seek shelter immediately. The safest place to be during a tornado is an underground storm shelter or a windowless interior room on the lowest floor of a building. Mobile homes and vehicles are particularly dangerous in a tornado, as they can be easily lifted or overturned by strong winds. Tornado research continues to advance, with scientists using radar, satellite data, and even storm-chasing teams to gather more information about how tornadoes form and evolve. Understanding these storms helps improve forecasting, giving people more time to prepare and take shelter. Tornadoes may be short-lived, but their impact can last for years. By studying how they form, move, and dissipate, meteorologists and researchers work toward better prediction methods to save lives and reduce destruction. While we cannot stop tornadoes from occurring, knowledge and preparation are the best defenses against their devastating power. Earthquakes are one of the most powerful natural forces on Earth, capable of reshaping the land in a matter of seconds. They happen when energy that has been building up underground is suddenly released, sending shockwaves through the Earth's crust. This energy release is caused by the movement of massive slabs of rock beneath the surface, known as tectonic plates. These plates are always shifting, though usually at a slow and steady pace. However, when they get stuck against each other, pressure builds up over time. Eventually, the stress becomes too great and the plates suddenly slip, releasing a huge amount of energy in the form of an earthquake. The place where this movement happens is called a fault line. Faults are cracks in the Earth's crust where plates meet and interact. Some faults slowly creep over time, while others remain locked in place for decades or even centuries before releasing built-up energy all at once. The exact location underground where an earthquake begins is called the focus, and the point directly above it on the surface is known as the epicenter. The closer a place is to the epicenter, the stronger the shaking tends to be. The strength of an earthquake is measured using the moment magnitude scale, which scientists use to calculate the total energy released. The shaking caused by an earthquake can vary widely from small tremors that go unnoticed to massive quakes that bring down buildings and reshape landscapes. Some earthquakes cause the ground to rupture visibly, splitting roads and shifting entire sections of land. Others occur deep beneath the surface, shaking the ground without leaving any visible cracks. Earthquakes can happen anywhere, but they are most common along plate boundaries where tectonic plates meet and interact. One of the most active earthquake zones in the world is the Pacific Ring of Fire, a horseshoe-shaped region that stretches around the edges of the Pacific Ocean. This area is home to some of the most powerful earthquakes ever recorded, as well as frequent volcanic eruptions. Other regions like the Himalayas experience earthquakes due to the ongoing collision of large continental plates. Even though earthquakes can be sudden and unpredictable, scientists have been studying them for decades to better understand their causes and effects. By monitoring fault lines and measuring ground movements, researchers can identify high-risk areas and improve earthquake preparedness. While it is not yet possible to predict exactly when an earthquake will occur, understanding how they happen is a crucial step in reducing their impact. When an earthquake occurs, the energy released travels through the ground in the form of seismic waves. These waves move outward from the focus, shaking the Earth's surface and structures above. There are different types of seismic waves, each affecting the ground in unique ways. The first waves to be detected are called primary waves, or P waves. These waves travel the fastest and move in a push-pull motion, similar to how sound waves move through air. Because they are the first to arrive, P waves are often used in early warning systems to provide a few seconds of advance notice before stronger shaking begins. Following closely behind are secondary waves, or S waves, which move more slowly but cause much more damage. Unlike P waves, which travel in a straight line, S waves move in a side-to-side motion, shaking the ground horizontally and making buildings sway. In addition to P waves and S waves, surface waves are another major factor in the path of destruction caused by earthquakes. These waves travel along the Earth's surface rather than through its interior, and they move in a rolling or rippling motion. Surface waves are responsible for the most intense shaking and can cause the ground to crack, buildings to collapse, and landslides to occur. Because they travel more slowly than P waves and S waves, the shaking from surface waves can last longer, especially in large earthquakes. The extent of destruction caused by an earthquake depends on several factors, including the magnitude of the quake, the depth at which it occurs, and the type of ground beneath the affected area. Earthquakes that occur at shallow depths tend to cause the most damage, as the seismic waves have a less distance to travel before reaching the surface. Soft, loose soil can also amplify shaking, making structures more vulnerable to collapse, while solid rock can help absorb some of the energy. In urban areas, the effects of an earthquake can be devastating. Buildings, bridges, and roads are at risk of severe damage, especially if they were not designed to withstand strong shaking. Infrastructure failures, such as broken gas lines and electrical outages, can lead to fires and further destruction. In some cases, entire city blocks have been reduced to rubble within moments of a major earthquake. In addition to structural damage, earthquakes can also trigger natural disasters, like landslides and ground liquefaction, where soil temporarily behaves like a liquid, causing buildings and roads to sink. As scientists continue to study seismic activity, engineers and city planners use this knowledge to design buildings that are more resistant to earthquake damage. Seismic-resistant structures are built with flexible materials and special reinforcements that allow them to sway with the shaking, rather than collapse under the stress. Advances in early warning systems and emergency preparedness have also helped to reduce the risks associated with earthquakes, providing people with critical seconds to take cover before strong shaking begins. While seismic waves are responsible for the immediate shaking of an earthquake, their impact extends far beyond the initial tremors. One of the most dangerous secondary effects of earthquakes is the sudden displacement of land and water, leading to events like tsunamis and ground ruptures. Tsunamis occur when an earthquake shifts the ocean floor, displacing massive amounts of water. Unlike regular waves caused by wind, tsunamis move rapidly across the ocean as a series of powerful surges. When they reach shallow coastal waters, their speed decreases, but their height increases dramatically, often resulting in catastrophic flooding. Coastal regions near earthquake-prone zones, such as Japan and Indonesia, are particularly vulnerable to these deadly waves. Ground ruptures happen when the Earth's surface cracks or shifts due to the intense force of an earthquake. These ruptures can tear apart roads, railways, and pipelines, making transportation and emergency response efforts difficult. In some cases, entire sections of land have been lifted or dropped by several feet, permanently altering the landscape, Large fault lines such as the San Andreas Fault in California are known for producing significant ground displacement during major earthquakes. Another dangerous effect of earthquakes is soil liquefaction. This occurs when saturated soil loses its strength and behaves like a liquid due to intense shaking. Buildings and other structures on this unstable ground can tilt, sink, or collapse entirely. This phenomenon is especially common in areas with loose, water-saturated soil, such as river valleys and coastal regions. Liquefaction played a major role in the destruction seen during past earthquakes in places like New Zealand and Turkey. Landslides are also a serious risk in mountainous or hilly regions affected by earthquakes. When the ground shakes, loose rock and soil can break free, sending debris rushing downhill. These landslides can bury entire villages, block roads, and create long-term hazards by reshaping the terrain. Heavy rainfall following an earthquake can further destabilize slopes, increasing the risk of additional slides. The long-term effects of earthquakes extend beyond physical destruction. In the aftermath of a major quake, communities often face food and water shortages, power outages, and displacement of large populations. Rebuilding efforts can take years, and economic losses from infrastructure damage and business disruptions can be enormous. In some cases, earthquakes have permanently changed the way cities are built, leading to stricter building codes and improved disaster preparedness measures. Despite the destruction they cause, earthquakes have also played a crucial role in shaping the Earth's surface over millions of years. They contribute to the formation of mountains, valleys, and other geological features, constantly reshaping the planet. Scientists continue to study earthquakes in hopes of improving early warning systems and minimizing the loss of life in future events. As scientists continue to study earthquakes, advancements in technology have helped improve our ability to detect and respond to them. While earthquakes cannot yet be predicted with absolute certainty, early warning systems have been developed to provide crucial seconds of notice before strong shaking begins. These systems work by detecting the initial seismic waves that travel faster than the damaging ones, sending alerts to people and infrastructure so they can take cover or shut down critical operations. Countries like Japan and Mexico have some of the most advanced early warning networks, helping to reduce casualties and damage when major earthquakes strike. In addition to early warnings, earthquake-resistant construction has become an essential part of protecting people and buildings in high-risk areas. Engineers design structures with flexible foundations, reinforced materials, and shock-absorbing systems that allow buildings to withstand intense shaking. Some skyscrapers are built with counterweights or base isolators, which help reduce movement during an earthquake. Retrofitting older buildings with modern reinforcements is also an important strategy in minimizing destruction. Countries like Chile and Japan have some of the strictest earthquake-resistant building codes in the world due to their frequent seismic activity. Beyond engineering solutions, emergency preparedness plays a key role in reducing the impact of earthquakes. Governments and communities in earthquake-prone regions conduct regular drills to teach people how to respond when the ground begins to shake. Families are encouraged to have emergency kits with food, water, medical supplies, and communication tools in case of disruptions. Knowing how to drop, cover, and hold on during an earthquake can significantly increase survival chances, especially in densely populated areas. Although earthquakes can be devastating, they also serve as a reminder of the powerful forces constantly shaping our planet. Over millions of years, earthquakes have played a role in forming landscapes, creating mountain ranges, and even influencing climate patterns by altering ocean currents and atmospheric conditions. Scientists study past earthquakes to understand how they have shaped the world and use that knowledge to improve preparedness for future events. The study of earthquakes continues to evolve as researchers develop better monitoring systems, improved building techniques, and more effective disaster response strategies. While we may never be able to prevent earthquakes from happening, ongoing scientific advancements help us minimize their impact and protect lives. Understanding these natural events not only helps communities stay safer, but also deepens our knowledge of the ever-changing earth beneath our feet.